All right, morning chemists. Today then, I thought we would look at equilibrium, and we'll look at static equilibrium, dynamic equilibrium, open systems, closed systems, isolated systems, reversible reactions, irreversible reactions, and Alicia Taliyah's principle. So this is what I wanted, mic's on. This is what I wanted to do today. All right, so without further ado then, let's just have a little look then at equilibrium. And so, all right, equilibrium. Like so, equilibrium, all right. Yeah, I think I can write my M better than that. Hold on a minute. Got to get back into using my tablet here with bit paper. But look, equilibrium. All right. The classic one that they give you is this one. And so, all right, we've got copper sulfate like this. This is copper sulfate pentahydrate like this. And then they give you this little double-headed arrow thing. And then you've got copper sulfate on this side and water like so. Okay, so that's a copper, believe it or not. So this is the one that something like this, they normally put this on the board. Your teacher normally puts this on the board and you're thinking, okay, well, what is this? All right, so what it is if I break this down into a different pen color, right, we'll just use green right now, that's fine. Okay, yeah, I think last year my students had named some of these colors like Kermit the Frog green and everything else. But what this means is, to the copper sulfate pentahydrate here, this reaction in blue means that it can proceed forward. And so you get copper sulfate and 5H2O. And it can also proceed backwards. So this is the forward reaction. This is the reverse reaction like this. And so we get this. So rather than write these two reactions out all the time, what they tend to do is you just add them together. Like so. And if you add them together back in blue, right here, the overall reaction is this one. So this is a type of reaction that they normally give you like this, and I'll explain what all the symbols mean in a minute. Like so, and just to be solid, to be perfectly correct. All right, but the equation states in on the top one. All right, and put them down here as well. Now, you say, okay, so your teacher probably put this on the board, and you say, right, well, what exactly does this mean? Well, this means in red. Up here, see this little symbol here. What this little symbol here means is that this is dynamic equilibrium. You say, well, hold on a minute. First off, what is equilibrium? And second off, well, what does it mean to be dynamic equilibrium? I'm going to see this on the board, all right? And your teacher may have done the one with the Haber process, which we do, you know, okay. Another classic one is hydrogen and iodine. So, yeah, okay, got that, Graham, got that. But what exactly is dynamic equilibrium? Well, equilibrium, first off, chemists, equilibrium means that you're in balance, right? Real simple explanation. Equilibrium, you're in balance. You see somebody walking down the street, they're in equilibrium because they're standing upright and they're walking down the street. That is in equilibrium, right? On the other hand, maybe you see them coming out of a bar or a pub and they're a little drunk. And at this time, you're thinking, well, maybe they're not in equilibrium because they're staggering all over the place, like this, trying to stand upright, staggering around, looking for something to hold on to. Maybe they're drunk, a little tipsy, a little intoxicated. They're not in equilibrium. We say, well, no, they're about to fall over, aren't they? All right. So equilibrium then, all the equilibrium means is just balance. All equilibrium means is nothing more than balance. All right. Now, another example, nature, the circle of life. Dare I say the Lion King? All right. So I use this example, the Lion King, and I've got to preface this one. After I saw the Lion King, I said to myself, I'm never going to watch a Disney movie again. Why? Because I don't know. I mean, I saw the movie when it came out, and it was on a date, and you got the popcorn and you got the soda. I was back in the States, got the popcorn, the soda, and everything else. You sit down, and about 10 minutes in, the lion dies. And you're thinking, oh, what's the point of paying all this money just to feel sad, right? Didn't really appreciate that one. So yeah, ever since then in chemistry, I've really I don't watch Disney movies. But what does the Lion King have to do with equilibrium? Well, it's because there's a balance in nature, isn't it? I was reading a newspaper article up in Scotland. They are introducing the grey wolf back into the population because they want to control the deer. So you're thinking, right, there's an equilibrium between the deer and what the deer eat, the flora and the fauna. No, this isn't A-level biology. But if there's nothing to keep the equilibrium, the balance in check between the deer and the fauna, and the flora and the fauna, well, then what they're going to do is that they become overpopulated. And so now they bring in these gray wolves. And the idea is that the gray wolves eat the deer, and then there's a balance, there's an equilibrium between the gray wolf and the deer and whatever the deer eat. And so you got this closed system, which I'll get into in a minute, but you're thinking there's a balance. Okay, so equilibrium then, think Lion King, think grey wolves up in Scotland, is just nothing more than a balance between two things. Now, dynamic equilibrium, all right, it's a balance between, back into chemistry then, because a balance, can I say, between the reactants and products. Right, this is what we're really talking about then with equilibrium. It's a balance between the reactants, what's on the left-hand side, and the products, what's on the right-hand side. Dynamic equilibrium, well, dynamic means that it's a reversible reaction like this. My pen is not behaving itself today as much as I wanted to, but it's okay. All right, it's a reversible reaction then between the forward reaction, forward, and the reverse reaction, backwards. So it isn't static. It isn't like all of a sudden it just stops. No, at equilibrium, there's copper sulfate pentahydrate going into copper sulfate and water, and copper sulfate and water going into copper sulfate pentahydrate. All right, so dynamic means that it's changing. I think the other one you can use is if somebody is walking up a down escalator. I know it's a weird one to use. You're walking up a down escalator. They're in dynamic equilibrium. Why? Because they're going up the escalator's going down. And if you're on the side looking in, you're thinking, well, to you, it would look like they're not actually moving, but they're actually going up a down escalator. And of course, the escalator's going down. So this then is dynamic equilibrium. Now, you're thinking, well, all right, this is dynamic, and this is the one that is on A-level, right here. I tell you right now, this is A-level, is what they'll ask you about. The other one then, really quick, you're thinking is a static equilibrium. All right, so you think static equilibrium. All right, chemistry version. Chemistry version would be Ding, ding, ding. What about carbon in the diamond? Let's do carbon the diamond. Hold on. So carbon in the diamond state. And I got to change my pen color. I got to keep things organized. Red looks like a little bit serious, you know, like, oh dear. Right, so look. What it is then is that you've got carbon in the diamond state. Is in equilibrium, right? Is in equilibrium with carbon in the graphite. That's graphite. So what this means then is, yes, because it's so energetically unfavorable to go from graphite to diamond, you know, and diamond to graphite in year 13, we talk about Gibbs free energy and entropy and enthalpy and everything else. This is an example of static equilibrium, meaning that, yes, there is diamond on the left-hand side of the arrows and there's graphite on the right-hand side, yes, but there's a balance, true, but they're not moving, you know, they're kind of like stuck, you know, they're not, it's so energetically unfavorable. All right, so this one would be static equilibrium. An example of static equilibrium then, going back to the example of the escalator, would be if somebody is just standing on the escalator, like the escalator is stationary, it's stopped, it's not moving, and someone's standing on the bottom stair, and then you're looking at that person from the side, probably wonder what they're doing, but you're thinking, yeah, this is an example of static equilibrium, because they're in balance, yes, but nothing is moving. Right. So anyway, equilibrium then is just a balance between the left and right-hand side, reactants and products. Dynamic equilibrium is the one that we studied at A level. It is when there is a forward reaction and a reverse reaction at the same time. Static equilibrium, yeah, we don't really get into this. There's not too much you can do with it. Like diamond to graphite. All right, now, a few more definitions, and I'm going to move my video feed over here. A few more definitions then would be, your teacher may ask you about a closed system. All right, so a closed system, and again, chemists, to be fair, you're only going to be looking at closed systems. A closed system really, well, a good example of a closed system right here. Here's my bottle of water here. And Buxton water, I don't know, bottled out of a tap and then, you know, sold to you by the wonderful folks at Tesco's. All right, here we are then, Buxton water, right? The closed system, right? Because it's got the lid on it, right? Or maybe if you go down to your favorite coffee shop, you know, Starbucks, Costa Coffee, and you get a cup of coffee and got the lid on it, you know, the little swivel stick thing in to make sure nothing can get out. That's a closed system. Why? Because a closed system means this. So here's my coffee cup like this. Enthalpy, heat, yeah, heat can move. Enthalpy, energy, heat can move in and out. Right, thinking your cup of coffee from Costa Coffee, Starbucks, does it cool down? Yes, it does. You walk around with it and the coffee's going to cool down. It's a closed system. The heat, the energy can leave the system. And then if you wanted to, you could always put it into the microwave and heat it up and you put energy back in, right? So enthalpy is what we talk about A level, and the closed system can move in and out. All right, here's my coffee cup like this. But matter or mass it can't move, cannot be lost. So what do I mean by this? Right, the reason why they put the lid on and the little swivel stick in is so that you can't spill the coffee. So it's a closed system. Matter, mass, cannot get in and out of the coffee cup. but heat energy can. All right, so back into chemistry then, this one over here, all right, all the systems they do at A level, they're closed systems. Why? Because equilibrium doesn't work in an open system. So this is the closed system right there. Hold on, chemist. All right, I can write the word system a little bit better than that. All right, so closed system, they're all closed system, meaning that they're in probably a round bottom flask with the stopper on it, or you know, in a jar with a lid on it. They're a closed system. An open system then is, well, it's simple. It's something without the lid on. So open system, for example, would be a beaker like this. Yeah, beaker, coffee cup. Beaker. All right. You know, some kind of a solution in open system. Now, an open system, you're thinking, can energy leave? Yes, you're thinking, so enthalpy, all right, can move in and out, true. You know, if you're doing the reaction, you put the beaker on the desktop, the bench in the lab, you're thinking, yes, it will cool down. So therefore, enthalpy, heat, energy can move in and out. And you're thinking matter, mass can be lost. So matter can be lost. It's like walking down the road, the street with a coffee cup without the lid on. If you trip on something like a pothole, something, you think, yeah, the coffee spills out. Okay. Same thing, the beaker in the bench, in the lab, if you tip it, well, then the chemicals, they go all over the bench, right? So closed systems are what we use for dynamic equilibrium then, all right? Dynamic equilibrium. We don't bother using open systems. And the other one is, why? Because they're not in equilibrium. Equilibrium like this. So you're thinking, right, got that now then. The other one, I'll put down here, the isolated system, don't even look at it all, is, for example, a flask. An isolated system is a flask. You know, a thermos. You're thinking, right, little flask right there. Okay, flask. All right. I'm going to put down enthalpy. And matter not gained or lost. Not gained or lost. So it's like one of the really, really fantastic flasks that, you know, you can't lose any, you can't lose heat. So like the coffee in the flask is never going to cool down. It's never going to warm up. You're not going to lose anything because it's got a really good seal on it. No, so we don't even bother looking at isolated systems. The only one we look at then is a closed system. So closed system right there. Now let's see. Hold on, I'm going to move my video feed down here so I can see what's going on. All right then, Kim. So I think what we're going to do then is let's look at Alicia Taliyah's principle. All right. So Alicia Taliyah's principle, like so. Ding, 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 ding. Right, here we are. I know I pronounce his name kind of weird, but anyway, Alicia Chatelier was a French scientist, and he came up with a principle. Now, first thing you got to do then, chemist, is this one. You're thinking what you got to do is you've got to get a definition down. And so I've seen so many definitions of this one. I've seen the one where the system moves to the side that reduces the stress applied to the system. All right, so I got this one from an an AQA text, it doesn't really matter if you do an AQA, Edexcel, whatever, exam board, Alicia Taliyah's principle is basically the same. Just look at your textbook to make sure you got it down, because as we know, definitions are, they're actually worth a letter grade. And so Alicia Taliyah then said, if a system at equilibrium is disturbed, it's bothered. Okay, all right. The equilibrium position, I'll explain what this means now. The equilibrium position, okay, moves in the direction that tends to reduce the disturbance. That tends to reduce the disturbance. And so this is one definition of it. So in green up here, all right, ding, 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 I will just stick with plain old green today. This is our definition, chemists. I can get my pen to write the word definition, hold on. All right, so this is our definition. So if you do need to learn the definition of it, please, right there, definition like so. All right, so you think, well, yeah, what exactly does it mean? Well, what it means is this is how I think about it. Imagine, and this is a real American example, I know. So here's a barrel, and there's a plank of wood on it. Plank of wood. I know. What we basically made is think seesaw. You know, down the park. Take my dog for a walk next down the park. You may see, like, you know, children playing on the seesaw, you know, two children, one on either end, and they go up and down like this. And basically, when you think about it, what it is that they're in equilibrium. And so here, all right, here is my, this little symbol right here. Okay, this is my equilibrium symbol. Like so, like an equilibrium symbol like this. Right, and yeah, I'm going to go ahead and just say this is my dynamic equilibrium like this. This is my dynamic equilibrium symbol. And so on one side, I've got reactants. And on the other side, I've got products, like so. All right, then. Now, equilibrium, we said, was when there's a balance between the left and the right-hand side. You know, Lion King, Circle of Life, deer up in Scotland, whatever, and copper sulfate, pentahydrate, goes to copper sulfate and water. Right, there is a balance between the left and right-hand side. So you're thinking, well, and this is a bit, I have a little think about this when it comes to I'm thinking like this. I guess, could I have this? And so here's my plank of wood, my seesaw. All right, here's my reactants. Here's my products. So imagine that you got the reactants of products inside your flask, and the reaction begins, and you come down to some kind of an equilibrium, right? So equilibrium, then you're thinking it's when, it is our definition of equilibrium, like actually what it is. And so equilibrium means that the rate of the forward reaction okay, equals the rate of the reverse reaction So in year 13, keep referencing year 13. In year 13, we get into Gibbs free energy and Arrhenius equations and enthalpy and entropy, but basically, which explains equilibrium in a bit more detail. But you're thinking equilibrium, then you got the reactants and the reaction begins, and I like to think that it rocks back and forth like this, kind of like a pendulum, you know, like a clock, like one of those old style clocks you may have seen in your grandparents' house. And eventually it comes to a stop, it comes to a balance. When the rate forward equals the rate backwards. Now, you could be, the equilibrium could be in balance when it's favoring the products. That's totally acceptable. It's in balance, it's in equilibrium, the rate forward equals the rate backwards. Okay, it's the very first part of the equilibrium. And I'm going to say the concentrations are constant. Now we've got to be really careful about this one, chemists. All right, this is quality of language. All right, do not say that they are the same. Because it's not true. Do not say that they are equal. Because it's not true. They are constant, which means that the concentrations are not changing. They kind of come to a final resting spot. And you're thinking, right, the concentrations are not changing, they're constant, what the word constant means, but you're thinking, it doesn't mean that the concentration of the reactants are the same as the concentration of the products. No, because in this example here, I've got the reactants favoring the products. They're not equal to each other. No, that's the wrong word to use. It's the constant. You're thinking, on this one then, my equilibrium position, and you've got to be careful here, chemist. My equilibrium position favors, got to put a U in, right, favors the right-hand side. Absolutely true, the products. The reason why I go on about this one is because you can't say the equilibrium favors the right-hand side. Why not? Lose my voice here. Because equilibrium means balance. It's actually correct. You can't say the balance favors the right-hand side. No, what you're saying is that the equilibrium position, all right, is favoring the right-hand side. Yes, and so it's moved, the equilibrium is in balance like this, reactants product is moving over to the right-hand side. It's favoring the products. True. It's like moved over, the position is shifted over to the right. Or you could have, here's my dynamic equilibrium symbol like this. You could have it where it is favoring, here's my reactants. And here's my products. You could have it where it's favoring the left-hand side. So I'll try and get a pen to write the word reactants a little bit more clear than that, chemists. Okay. All right. My equilibrium position all right, favors the left-hand side. Right, the reactants, true. But it's still it's still in equilibrium. It's still in balance. All right. It comes to like a final resting spot with the rate forward equals the rate backwards. The concentrations are constant. And then this is equilibrium. Or I guess the last one you could have then is kind of a weird one where it's like this. Reactants, products. Okay, hold on, I'm trying to get the pen to write the word product. Hold on, chemist. Reactant products like this. You're thinking, yes, it does. It's kind of in the middle. So you put down right the equilibrium, it doesn't favor either side. The equilibrium position doesn't favor. All right, can I get the word doesn't? Doesn't favor either side. No, it's just in the middle. I mean, this is a really strange set of circumstances. I mean, odd one, but technically, I guess it could be, right? So anyway, Leach's principle says that if I disturb the equilibrium, then the equilibrium position is going to either move to the product side or it's going to move to the reactant side in order to reduce the disturbance or remove the stress or applied to the system. I've seen so many versions of it, okay? Now, here we are then. Let's have a look then at a couple of examples that they'll probably give you. All right, they tend to basically stick chemists to, well, kind of like the same ones. All right, so the first one that you'll definitely see, and we'll get back into this one, all right, is you'll see the one with the Haber process. Because no cheesy chemistry jokes intended, but the exam board has to give you compound questions. Oh, I know, it's bad. But you're thinking, you know, where there's questions like multiple concepts rolled into it. That's what I mean by a compound question. And so they'll give you the one, and I'll do this one right here so that we can all see what's going on. Nitrogen and ammonia. Yeah, this is the Haber process. Like so. It was like World War II. They came up with it after World War II to make fertilizers and everything else. And right, but so they give you this one, right? So this is the Haber process, one of the typical ones that you'll see. So I got nitrogen and hydrogen giving me ammonia. And over here, they telling us that the enthalpy is negative 76 kilojoules per mole. All right, so very first thing I would do is straight off the bat, chemist in, all right, Florida orange, because this is negative, this is exothermic. I would put my enthalpy symbol on the right-hand side because exothermic means that you're producing heat. So I tend to think about it as being a product. It's going to be on the right-hand side. So the converse would be if this was endothermic, you're putting heat in, think of it as a reactant and put on the left-hand side. But anyway, let's see. Also, do you notice that they're always in... Ooh, let's try pink. All right, right here, look. They're always homogeneous. Like the systems you see at A level, they're always homogeneous, meaning in the same phase. So it's always a gas like this, like, you know, like always a gas like this one. It's just homogeneous, the same phase. Heterogeneous, just in case you want to know. Heterogeneous would be different phases. Different phase. So heterogeneous would be, for example, calcium carbonate chalk. Calcium carbonate is dynamic equilibrium in a closed system, yes, with calcium oxide and CO2. But we don't do heterogeneous systems like calcium carbonate at A level. That's university, so you don't have to worry about it. Anyway, on this one, if I turn my pen back to blue, right here, there's not too much they can actually ask. So the very first thing they're going to say is, well, what happens if you increase the pressure? Now, this is how I teach it. I say this, look, Alicia Taliyah's principle in a nutshell, the equilibrium moves away from the side you add. And for my A-level English people, they'll say alliteration like the A and the A add up, or toward the side you take away from. So this is not the definition of Alicia Taliyah's principle, but it's a good working, I don't know, like process, right? Like thought pattern away from the side you add. So on this side, then I've got over here, by the way, I've got 1 and 3. I've got 4 moles of gas like this, and on this side, obviously, I've got gas in quotes. No, doesn't matter what it is. I've got 4 moles of gas on this side. On this side, I've got 2 moles of gas. And so if I increase the pressure, then it's going to move to that side with less gas molecules. So my equilibrium position, here's my little symbol here, moves to the side with less gas molecules. With less moles of gas. All right, hold on, less moles of gas. In order to remove the disturbance to the equilibrium and move that side that reduces the stress, the disturbance, okay? So you're thinking, yes, if I got 4 moles of gas on the left, I've got 2 moles of gas on the right, my equilibrium position is going to move to the right-hand side. So you write down your equilibrium position moves to the right-hand side. Right, the products. And so they like to ask about the pressure. So obviously, if I decrease the pressure, it would move in the other direction, right? If you decrease the pressure, the equilibrium position would move to the left-hand side, the reactants, because you have less moles of gas on the left-hand side. All right, so the pressure one then, it's kind of standard, all right? Now, the A-star question is with the temperature. They're always going to ask you about the temperature, Kim. So I tell you right now, no matter what exam board you're on, they're always going to ask you about the temperature. And so this is the reason why when I teach, they go, right, if it's exothermic, you put the little enthalpy symbol right there. Because then you think of the enthalpy as being a product. And if you increase the temperature, I mean, obviously, this depends on the system. If you increase the pressure, so going in this direction, obviously, this is exo. You're putting the heat coming out, and this way is endo. But point being is, if you increase the temperature, it's like you're adding heat in, which means the equilibrium position is going to move to that side. all right, away from the side you had. It's going to move to the other side to rebalance the equilibrium. And so if I increase the temperature, then my equilibrium position, because it's exo, is going to move to the left-hand side, which is the reactants. And if I decrease the temperature, because they will ask you one about temperature. All right, well, if I was making an exam, I put on that. All right, increase the temperature. Then if you decrease the temperature, the equilibrium position is going to move to the right-hand side and you form more products. Okay, so classic one then is pressure and temperature. All right, these are the two that they're going to ask you, okay? It's always going to be a homogeneous system. The temperature one is the one that I would really look into to make sure I understand that this one. There's this example here. Let's see. Now, another one. We'll do two more. All right. Again, chemists, look, these are just classic. All right. So N2O4 in the gas state. No, on YouTube, you know, either your chemistry teacher has a YouTube video clip of this. We used to be able to do it in the classroom. This is what everyone should be thinking, you know, you take NO2 and you put it into, you could put it into, for example, like a gas syringe. And then if you increase the pressure on it, then it moves to the other side. And if you decrease the pressure, it moves to the other side. And so this has to do with pressure. The one that the reason why they enjoy doing this one is that you do see a color change. Okay. So anyway, on this one, this is the classic. This is your dinitrogen tetroxide going to nitrogen dioxide here. If you increase the pressure, this is easy, right? If you increase the pressure, I've got 2 moles of gas on this side, 1 mole of gas on this side. My equilibrium position, why it's dynamic symbol here, right? Homogeneous, yes. Assumed closed system. Is my equilibrium position is going to move to the left-hand side and you make more reactants. Or if you decrease the pressure, well, then it's going to move to the right-hand side and make more products, okay? This is one you've probably seen. Now, a tricky one, go, yeah, okay, Graham, I got so far, yeah, got it, yeah, right, you know, you just increase the pressure, decrease the pressure, whatever temperature, but this one here, this is one that you may see either embedded into a question or possibly a multiple choice, but something simple like this. You got hydrogen and iodine like this, and then it's in dynamic equilibrium. You go, okay, yeah, got it so far, hydrogen iodide. And then they say, well, what happens if you increase the pressure? And you go, well, hold on. I got 2 moles of gas on this side, right? You know, combined. And of course, I've got 2 moles of gas on this side. And you're thinking, oh, well, that's a good question, because if I increase the pressure, the equilibrium position is not going to move. Why? Because you got the same number of moles of gas on the left and right-hand side. So if you increase the pressure, you would say there's no change in the equilibrium position. All right, nothing happens. All right, so this one, be careful of this one. This is a classic because they would put this on to go see if you really understand about equilibrium position. All right, so having said that, chemists, that is Alicia Taliyah's principle in a nutshell. Went over the definitions. Oh, one more thing we've got to do before I forget is if you change the concentration, so square brackets, if you change the concentration, this is one that possibly a multiple choice, but really, no, we wouldn't see this one on the exam because, well, you know, it's a bit easy. But if I look at the one with hydrogen and iodine, right, if I increase the concentration, how I do it is, again, you think, right, equilibrium position, all right, here's my barrel, plank of wood, seesaw. If I increase the concentration of hydrogen, then it's like I'm adding a reactant, and so my equilibrium position is going to move over to the right-hand side, and you're going to form more product. And we'll get into this one now when we talk about the Haber process, okay? Or the other one could be if you take away, let's say that you took away hydrogen iodide, all right? Well, then you're thinking this one, the top one with hydrogen, is away from the side you add. Like, you know, you increase the concentration of hydrogen, the equilibrium position moves over to the right-hand side. Got it. Hydrogen iodide, if you decrease the concentration of hydrogen iodide, like you took it out of the system somehow, then you're thinking the equilibrium position is going to move over to the right-hand side because it's toward the side you take away from. All right, again, you would form more product. Right then. So I tell you what, let's have a little look then at some difficult questions. Here we are. All right, so this one here then, all right. The hydrogen used in the Haber process. Yes, chemists, by the way, there's so many systems you need to know for equilibria. Like they look at the spec, there's like so many systems you just need to know. This is one of them, all right. They give you the system, but what I'm saying is when you're revising for your UCAS exam or your year 13 final exam, you're thinking, make sure you do plenty of the questions that's going to be the type of systems that you'll see on the exam. And this is one of them. All right, then here we are then. Let's see. This one strangely has been duplicated, don't know why. All right. Let's see. This is ding, ding, ding. Right, so right here, straight off the bat, then this one is endothermic. And so what I'm going to do is I'm going to put my enthalpy symbol on this side. So on the previous one we did, you know, with the Haber process, the previous one we did was exothermic. So the enthalpy symbol was on the right as a product. This is now endothermic. So my enthalpy symbol is on the left-hand side because it's like a reactant. Let's say, now if I increase the pressure, all right, so straight off the bat to go, I've got 2 moles of gas on this side. And on this side, I've got 4 moles of gas. Okay, so if I increase the pressure, then what's going to happen is I'm going to, hold on, get rid of this right here. If I increase the pressure, I'm going to move my equilibrium position, quality language, equilibrium position over to the left-hand side, LHS, left-hand side, and form more reactants. Okay, because you're trying to keep the equilibrium the same by moving the position, all right? So you're thinking to go move over this side to get away from, if you're stressing the right-hand side, to move over the left-hand side. Now, again, chemists, if I was revising this one, what I would do is I would make sure I knew how to do the temperature one. So on this one, the previous one was exothermic. I picked this one to make it endothermic. If I increase the temperature, right, increase the temperature, it's like I am here, increase the temperature. Increase the temperature, it's like I'm adding a reactant. I think like temperature as a reactant, therefore my enthalpy is going to move over to the right hand. So my enthalpy, if I increase the temperature, I'm going to move the system over to the right-hand side. All right, so increase temperature, my equilibrium position moves over to the right-hand side, all right, because it's like, imagine I'm pushing up on the enthalpy symbol and everything sliding over to the right. So right-hand side, I'm making more product, like so. All right. Let's say, or I guess they could ask you, let me make sure we got the one with temperature correct. If I decrease the temperature, and so I can taking away the enthalpy, then my equilibrium position is going to move over to the left-hand side, and I'm going to make more reactants. Okay, so there you are. One example was exothermic, one example with endothermic. The pressure one, I think, is fairly obvious. The one with the concentration, well, you know, like, for example, if I increase the concentration of methane, well, then what's going to happen? My equilibrium position is going to move over to the right-hand side and form more products. Okay. All right. So this is Alicia Taliyah's principle. Like this one, let's say, oh, now this one, I picked this one in chemistry because this one is a bit tricky. All right, so this one here says when bismuth chloride is added to water, a reaction occurs and a white precipitate forms. White precipitate like this. Hold on. Ding, ding, ding. White precipitate forms, okay. The following equilibrium mixture is set up. Yes, all right. So we don't do heterogeneous systems at A level, but they give us this one. Okay. And it said, what would be the effect on the amount of precipitate, all right, if sodium hydroxide solution is added to the mixture? And you go, oh, hold on. All right, sodium hydroxide. All right, so thinking sodium hydroxide chems like this. First thing I would ask is, well, what exactly can sodium hydroxide react with? The HCl, you know, alkaline. HCl, like so, acid is going to give me, well, you know, acid and base, salt plus water. All right. Okay, so you're thinking, all right, so it's going to react with the HCl. Well, what does that mean? What that means then is, in Syracuse orange, this means that I am removing, I'll put down the sodium hydroxide removes the HCl. So my sodium hydroxide effectively removes, because it reacts with it, and the sodium chloride is not present in the system here, removes the HCl toward the side you take away from. So therefore, I'm going to say my equilibrium position moves to the right-hand side, which means I make more product. And because I make more product, then my concentration of my precipitate increases. And so what's the observation that you would see? Therefore, you would say more precipitate formed. Right. So this one then, I picked this one. It's a nice little chemistry question right there. Just shows what happens, you know, a typical system here, right? So you can, I would say that you would remove the HCl, the sodium hydroxide reacts with the acid, you remove the HCl, all right? Now, another way of looking at it is that you can also say that you produce water. In this reaction, you increase the water, and so therefore the equilibrium position is again going to move to the right-hand side. Myself, I would stick with this one. This is the one that this is a chemistry bit, isn't it? So the fact you produce water, well, you know, it's like, okay, and technically, yes, there is water on this side, so it's away from the side you add. All right, towards the side you take away from. So yes, it would, the equilibrium position would move over to the right-hand side, but stick with the chemistry one. So this is what they wanted, because I think this was a 2 marker. All right. So application of Alicia Taliyah's principle there. Now then, on this one, right, here we are in chemistry. Now look, this one is going to be on the exam, guarantee it. Yeah, so the Haber process is going to be on the exam. So again, you know, I keep saying, well, what you got to do is you do need, make this a little bit big so you can see it right here. You do need to learn various systems, you know, like the Haber process, the production of hydrogen, whatever. All right, this one here then. Now we've done this one at the start of the lesson. We did this one, right? So you got this one. You see this weird looking graph, and then they say, well, this is an industrial application. Yes, 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 it is. I mean, you produce ammonia, right? And then you see this weird looking graph, and then what they do is that they talk about pressure and they talk about temperature. And so the very first thing that you need to know is that we're going to be using, I'm going to change pattern colors, hold on, because I don't know, I like blue. Orange is kind of a weird one to be writing in. Look, so what you need to do then is this one. You need to learn the compromise or memorize the compromise pressure and temperature. You say compromise pressure and temperature. Yeah, compromise kind of means, oh, you know, you're trying to negotiate something, aren't you? You're saying, well, yeah, I'll make a compromise. And so, yeah, there's a compromise, there's a kind of a happy medium between pressure and temperature, because if you will look at the pressure, all right, you say, if you look at this system here, you say, well, if I wanted to make as much ammonia as possible, what I should be doing is I should be increasing the pressure, shouldn't I? Because you say, well, there's 4 moles of gas on the left, total, and there's 2 moles on the right. So therefore, if I wanted to shift the equilibrium position all the way over to the right-hand side to make as much ammonia as possible, this is in industry, you're thinking, well, what I should be having is I should be having as high a pressure as possible. That would make sense, right? Yeah, but problem is, all right, you're thinking problem is, if you had high pressure, yes, you would increase the yield of ammonia. So you say, yeah, increase the yield, the concentration of ammonia. And so you have a very high yield. Totally agree with that one. But only one problem is the high pressure, all right, means you need more expensive apparatus. And so cost becomes a factor, doesn't it? You know, you're thinking, yeah, in industry, yes, if you increase the pressure, you can make as much ammonia as you possibly can, yeah, but the problem is that you need more expensive apparatus, you know, pipes and reaction vessels and everything else. And so it does become cost effective. Now, on this one, Chems, I would stay away from safety because, yeah, it is true, but go for the expensive apparatus. You don't want expensive apparatus, all right? So therefore, the compromise pressure is 200 atmospheres. So you pick 200 atmospheres. It's a compromise. Not low pressure, not high pressure, but you're thinking, yeah, kind of in the middle. Now, the other one then is you think the temperature. Now you think, aha, right, well, temperature, hold on. Graham said that, you know, dun, right there. Exothermic, I know to put my enthalpy symbol on the left-hand side there. You got that bit, right. Now, problem is, if I increase the temperature, all right, away from the side you add, the higher the temperature, it means my equilibrium position is going to go to the left-hand side. Oh. And so if you had high temperature, then your equilibrium position moves over to the left-hand side. And so therefore you decrease the concentration of ammonia. Therefore you decrease the yield. Oh, you think, well, I know, let me lower the temperature. I mean, if you lowered the temperature, well, then the equilibrium position would move over to the right-hand side. And you're thinking, well, there you are, look, you know, I increased the concentration of ammonia, I increase the yield. True, but problem, and this one goes into energetics, all right, chemists. If you decrease the temperature, think Maxwell-Boltzmann. Oh no, he's linking into Maxwell-Boltzmann. I am, look. Yeah, I know, it's not the perfect Maxwell-Boltzmann curve, it's okay. Right, look. Right there. Here's my activation energy. Yeah, you know that if you lower the temperature, then I'll try to do this one in green. This is not like the most perfect. It's kind of pretty awful actually, but anyway, look, point being is that if you lower the temperature, all right, then number of molecules and energy, then less molecules have energy greater than or equal to the activation energy, so the rate goes down. So yes, and so at lower temperature, the problem is that you decrease your rate. Oh no. So yeah, if you lower the temperature, it does go to the left-hand side, true. But problem is that you're thinking, you end up decreasing the rate of reaction. So you're there all day. And again, in industry, time is money. So you're thinking, no. All right, then. So what you do is that you pick a compromised temperature. And so you pick, right there, ding, and 450 degrees. And so you see this one, see the 450 degrees. All right, and you see the 200 atmospheres like so. These are your compromised pressure and temperature. You just need to know this. All right, and if they ask you why, well, because, and I'm just about there trying to get a big blue dot going there. If you increase the pressure too much, then you run into the problem of, yes, you do increase the yield, but then it costs you so much money. Expensive apparatus is not going to be worthwhile. Or if you increase the temperature too much, well, then what happens is, yes, you increase the rate, but the yield goes down. And so again, you see chemistry, it always seems to become this temperature one seems to be with us during this entire lesson, doesn't it? You're thinking, yeah, all right, so temperature. So on this one, make sure that you understand that if you lower the temperature too much, then you increase the yield, true. If you increase the temperature, you decrease the yield, but you, if you increase the temperature, you decrease the yield, but you increase the rate. And so link in your answer, link rate and yield together. Okay. When you're talking about the temperature one and the pressure one's easy. All right, now here we are then. I did this one and also, oh, this one. Now this one here, chemist. This is the good one, right? Yeah, I pulled this one. All right. So let's go take a look then. All right. Sulfur trioxide decomposes to form sulfur dioxide and oxygen at temperature T1 according to the equilibrium shown. Right. And so I'm going to doodle this one over here. so that we can have a good look at it. So we think in homogeneous system, yeah, typical A level, dynamic equilibrium, they always are. Closed system, yes, means a sealed vessel. Okay, like this. And they're saying that it's endothermic, so I'm just going to put my enthalpy on this side here. All right, then. It said, state the time to nearest minute when equilibrium is first established. And so what they're getting at is at equilibrium, okay, the rate forward, as in the SO3, giving you the SO2 and O2, is equal to the reverse reaction, the rate backwards. Right then. No, yeah, okay, got that. But how does this link into the graph? Because recall, right? Recall from GCSE, right? The gradient, the slope, is that not equal to the rate? You'd say, well, okay, why? Well, because rate isn't rate equal to the change in concentration over the change in time. All right, change in time. I'll put my little delta symbol there for change of concentration. So in other words, all we've got to do then, chemists, is this one. We just got to find out when the rate forward equals the rate backwards. Well, you're thinking, if I'm looking at this dotted line here, the rate's changing, it's going down, yes, yes, yes. And then, it just seems to, look, it seems to kind of like equalize out just around the 3-minute mark. It seems to be like the rate just seems to be, well, the rate at the 3-minute mark is this, isn't it? Is 0. All right. So what I'm saying is, if I doodle on this one, all right, is obviously the rate is decreasing. The dotted line, the rate is decreasing. Yes, yes, yes. And on the solid line, the rate is increasing. Yes, yes, yes. So you're thinking the rate forward can't be equal to the rate backward when the dotted line is decreasing in rate and the curved line is increasing in rate. What I need to do is find the very first instance on the graph when the rates equal, and that would be when they begin to be horizontal, which to me is at 3 minutes. All right, so if I was going to explain this one, I would say the rate at equilibrium, the rate forward equals the rate backwards. And you know that the rate is change in concentration, the change in time. And so at the 3-minute mark, doesn't matter which one you pick, the rate is equal to 0, which means that you're at equilibrium. This is when equilibrium is established. Right. So, okay, yeah, that was easy. Right, here we are then. It says sketch on the graph. I have to go back in the graph now. Sketch on the graph above how the concentration of sulfur dioxide changes over the 6 minutes at temperature T1. Ooh, okay, hold on a minute, chemist. They wanted sulfur dioxide, right? SO2. All right, then. So here we are, SO2 like this. Now, you're thinking, right, chemist, would you agree? All right, so obviously the dotted line going down, yeah, this is your SO3. And the curved line going up, this is the O2. And so they want to know the concentration of SO2 over 6 minutes, right? So I'm thinking, ding, 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 ding. Would you agree that there is a 2-to-1 ratio between SO2 and O2? Don't know what's going on with my pen this morning, chemist. I don't know, right? It's a 2-to-1 ratio. So therefore, SO2 must be double O2. All right, so if I'm looking at this one in chemistry, I may have to appear your computer screen here, but I make the O2, this is 0.15 like this. And so if O2 is 0.15 at equilibrium, then SO2 must be double that. SO2 must be 0.3. It's double it, 1:2 ratio. All right, then, so I'm going to extend my equilibrium line up like this. Now, it has to establish equilibrium at the same time as SO3 and O2 does. And so I'm thinking right here has to be equilibrium is established. And so it's going to be a straight line after that. And then you just got to curve it down. Whoops. Maybe a little bit better than that, but look. All right, you've got to curve it down. And so you kind of get this, like this. And so this is, yeah, good enough, right? You're saying you get, understand the principle that at equilibrium, SO2 has to be double O2. This is where the 0.3 comes in because it's double 0.15. And you're understanding that this is when equilibrium is established. Right, and so you're thinking, yeah, this is SO2, okay? Let's say, so I've done this one, right? So I'll put down C, previous page, we've done this one. All right then, chemists. The temperature of the mixture was changed to T2, okay, and the mixture left to establish a new equilibrium. Right, now, by the way, all right, got a point that straight off the bat, came straight off the bat here, right? Equilibrium, and we'll get into this next time, right, is established at a given temperature. Okay. Meaning, if you change the temperature, then you change the equilibrium. The system is going to move until, you know, you reestablish equilibrium. Okay, we'll get into this one next time. So anyway, change to T2, and the mixture left established a new equilibrium. In the new equilibrium mixture, the concentration of sulfur trioxide was found to be 0.07. So hold on, got to keep this straight, right, chemists? This was 0.07 at T2. Right, hold on. This was 0.07, trioxide was 0.07 T2. Hold on. I think I put that in the wrong one. Hold on. Yep. Sulfur trioxide was 0.07 at T2. Okay. And, right, so, and they want to know which one's higher, T1 or T2 is higher. Okay, then. And so they did say then, so they're thinking, hold on. This is at T1, right? At sulfur trioxide at T1. Oh, sulfur trioxide at T1 from the graph right there is 0.1. All right. Okay. So they want to know which one was higher temperature, T1 or T2. All right. So chemists, again, look, they're going after the temperature one. And but we know to put our enthalpy symbol on the left-hand side for endothermic and right-hand side for exothermic. So here we are. At T2, SO3 is, the concentration is lower. So over here, I'm going to say, I'm going to move my video link over here. At T2, the concentration of SO3 is lower, it's gone down, right? It's 0.07 as compared to 0.1. So therefore, this means that the equilibrium position, well, let's take a look. The equilibrium position, if I got less of this, then I move my equilibrium over to the right-hand side. All right, so my equilibrium position has moved over to the right-hand side, forming more products and less reactants. Right, by that. And so you're thinking, right, T2 is the concentration of SO3 is 0.7 at T2 and 0.1 at T1. Therefore, I must move the equilibrium position over to the right-hand side, making this go down. So therefore, I must have increased the temperature, right? I think now, if I increase the temperature, the enthalpy moves over to the right-hand side, away from the side you had, right? So therefore, I must have increased the temperature, all right, to make the equilibrium position move over to the right-hand side, because it's endothermic. So therefore, T2 must be higher than T1. There we go. Higher temperature is T2. Okay, so here we are in chemists right there. Hold on, I'm trying to get pen back here. So this one here, then chemists right there. Again, temperature, isn't it, guys? All right, then. So here we are then. What I'm thinking is we've done well today. We looked at equilibrium and we looked at, well, first off, we looked at closed systems, open systems, isolated systems, dynamic equilibrium, static equilibrium. We looked at Alicia Chatellier's principle. We've got the definition down. And then we looked, the working version I use is away from the side you add towards the side you take away from. So we looked at what happens if you increase the concentration, decrease the concentration, yes. And also the one with the pressure, okay? And you're thinking, you know, increase the pressure, decrease the pressure, it's going to move to that side, all right, to relieve the stress, okay? So the pressure one. But we spend most of our time looking at the one with temperature, because that's where the A-star question is, chemists, okay? And we did this one, all right? So we did one with exothermic, one with endothermic systems, and then we did this one. I picked this one because you'll link it into the graph, all right? Because it'll ask you to graph this one, fairly straightforward. And we established the equilibrium right there is when the rate forward equals the rate backwards, and that the concentration of the reactant of products is constant. All right. So I think we've done well today. Now, yeah, the sun's coming out at last. Yay, good. All right. So I'll take the dog to the park for a walk now. And then next time, what I thought we'd do is let's do some calculations. All right. So next time, we'll talk about the equilibrium constant, Kc, and we'll talk about how to write the Kc expression, products over reactants, raise the appropriate stoichiometric power, the indices, we'll do that one. And we'll do all the algebra questions, you know, like what's the final concentration at equilibrium of the reactants, the products. And also I'll do the one with what happens to Kc if you change the temperature. All right, chemists, so we've done well today. All right, hope you found that helpful. And I will see you next time when we look at Kc calculations. All right, so take care, be well, and I'll see you next time.